Okay, so I'm going to sort of start where Matt left off. So I almost started out working on this sort of stuff by chance. I was working on the Lima project. I had reverse engineered some the Molly instruction set and wanted to write a compiler for it. I got to the point where I had basically two backends. Both of them used SSA, as Matt mentioned. And in the end, I didn't want to have to translate into SSA in both of these backends and do the same optimizations. And I basically ran into sort of the same problem. So I went ahead and tried to implement SSA in GLSL IR. And it was interesting, but that's probably the most profitably or the most positive way you can put it is interesting. And I think it took Paul quite some time to actually understand what I had done. So it just turns out that trying to stick SSA into GLSL IR was really tough. And so when I went to FOSDEM to present on this, I mentioned the stuff I did a talk on Lima stuff, and I didn't even really mention this. But then I went to Ian's talk where he was like, yeah, we really need to do something about this. We really need to fix it. And then during the same presentation, I got an email saying, like, Paul had reviewed my stuff, and he was like, hey, why don't you come and work for Intel over the summer? I was like, great, cool, great. That's like a really nice opportunity. But what am I going to do? And so I thought about that. I thought about my work with GLSL IR and trying to convert it to SSA, and I was like, well, I could keep going down this road of modifying GLSL IR and like piece by piece, sort of doing what Ian had wanted to do and replace it until it became. But by the end of doing that process, I would wind up with something that was basically an entire new IR. And so why would I just do it like that when I could start from scratch instead and get basically the same result? So I decided to make a new IR, which I very inventively named new IR, or NIR. So there were a couple of goals that I followed when I wanted to start designing this thing. Of course, it had to be flat and SSA-based, like Matt already talked about. It had to have basic blocks, which is, and it had to have a control flow graph. And basic block is just a list of instructions that you go from start to end all the time, every single time. And modern compilers always have a control flow graph, which is just a graph of basic blocks. And that's how they represent functions. So I had to have that structure because every single compiler paper ever assumes that you have that. And like I ran into with trying to convert GLSL IR to SSA, if you don't have that, it's really, really hard to work with. So I had to do that. But I also had to preserve the original control flow structure. I had to have ifs in the IR. I had to have loops in the IR because that's, in the end, is what the GPU wants to consume. It doesn't care about basic blocks, even though the compiler optimization patches do. So I wanted to do the same optimizations before and after linking, which meant that I had to include a lot of high-level things that GLSL IR did include. I had to include a lot of like source-level semantics in GLSL so that we could eventually get to the point where we do linking in NIR, and then we do the same optimizations before and after linking. But I also wanted to support didn't want people who were writing backends to have to do too much transformation to get from NIR to their backend. So there are some things I added in there that are more conveniences, and I'll talk more about that later. And so, of course, drivers are going to change. The GPU hardware is going to change. So we wanted to make it extensible so that we could support things in the future. But in the end, we don't want to keep extending it so that it supports everyone's hardware. Drivers will still need a separate backend IR, and they're still going to need to do scheduling and register allocation and handling wacky hardware things in their own driver. There's really nothing you can do about it, as far as I can tell. All right, so I'm going to start off talking about more technical things about how it's actually been implemented. I'm going to start off with control flow, which I mentioned before. So on the left here is a really simple portion of a GLSL shader, and this is how it might be represented in the compiler. So you have a tree, that has loops and ifs, like I mentioned before, and that's sort of represented by the black arrows. And then the red arrows are the control flow graph. And in case it isn't obvious, which probably isn't, the red arrows are actually redundant. You can compute the control flow graph using the tree, but we keep both of those around in order to sort of optimize things, because all of the optimization passes want to use the control flow graph and think in terms of the control flow graph, but the backend needs to have the tree structure. So we keep both of those around at the same time, and then we have some help. I wrote some helper passes that deal with thinking. They deal with modifying the tree, and then as we modify the tree, we rewrite the control flow graph. So it winds up being not that bad that we've sort of duplicated information in the IR. And so one question that you might have as you look at this thing is, well, why do we have all of these empty basic blocks? It's as if we had, rather than just saying, oh, this thing always jumps here, so why do we have this empty basic block in between that's basically not doing anything? And the answer is that, first of all, it made the tree rewriting code that I mentioned earlier sort of easier, and it prevents a problem that comes when you do that, because you run into, if you don't include the empty basic blocks between ifs and loops, then you run into problems with critical edges. A critical edge is just an edge between two basic blocks in the control flow graph where you have more than one source leading to more than one destination. Most optimization passes really don't like this, and they just tell you at the very beginning, remove critical edges. And if you look at LLVM, it has a pass to do this, of course, and it does something like this. It just inserts a basic block and splits that critical edge in half. But this is a problem because now we no longer have structured control flow. And GPUs can't handle this anymore. You have to restructurize it somehow. So rather than doing that, whenever we rewrite the control flow graph, we make sure that we insert this extra padding, and that makes sure that we never run into those sort of problems in the first place. Okay, so this next part is probably the most controversial thing that came up when I initially proposed NIR, and it might be sort of difficult at times to explain it, but I'll try the best. So especially older GPUs had this traditional model where everything was in terms of 4 vectors, vectors with 4 components. And so if you wanted to have an array, you'd access it in terms of vectors of 4 components, and you'd index it in terms of that. And operations worked on those vectors of 4 components. And it was really sort of a pain for reasons that I'll get into soon. But we really still need to support it. And probably the biggest reason we need to still support it is that TGSI is entirely based around it, even though hardware is actually moving away from this model. So yay, TGSI. So if you look at what this traditional pipeline looks like, this isn't what people's hardware is actually like, but this is what DirectX bytecode looks like, and this is what TGSI looks like to some extent. You have a number of sources. You have a swizzle that can rearrange the sources in basically any order. Then you can optionally take the absolute value of some vector thing and then optionally negate the vector, or negate the floating point input. And because this was created when there was floating point, there wasn't really much thought given to integers at all. Then you run it through some ALU operation, you add them, multiply them, etc. You optionally saturate them, which just means clamp it to between 0 and 1. And then you finally write it out. And this is the most difficult bit. It's possible to only overwrite portions of the vector. And it turns out that when writing a compiler, this is really a pain. And we don't want to deal with it. And in fact, with SSA, it's basically impossible. You can't represent this in SSA because when you do partial updates, that means you have to write to the same register twice. And in SSA, the whole point is that you only write to each register once. So instead, in NIR and when I did this in GLSL IR, and probably what everyone else does, you have a way to combine the components of two SSA values. So rather than updating only the X and Y component, only the first two components, you take the old one and you take the new one and you combine the components. So the X and Y comes from the new and the Z and W comes from the old one. The problem with this is that getting out of SSA now becomes kind of tricky. You can trivially implement this by just doing a copy, but that's pretty inefficient. And figuring out when you don't have to do a copy is a difficult problem that no one's really solved before. And so if we ever want to use SSA optimizations on older backends like TGSI, this is a problem we're going to have to solve. Now, if you look at the NIR source code, it turns out it actually has all of this stuff in it. And you might be thinking, like, well, why? Like, this is terrible. Nobody wants this, but it's in there. And the reason is that while it might be easy for most backends to handle this, it's really not too easy for legacy backends like TGSI. We don't want them to have to do more than necessary. And if you think about it, so it would normally be pretty easy to handle these modifiers. They're just separate instructions, and in your backend that handles crazy hardware stuff, because we're in SSA, you just fold them in. And if you have SSA, that's really easy. If you don't have SSA, it's not. And if you have partial updating, it's even harder. So you need to do the folding before SSA, before you go out of SSA. But we also want a shared pass that goes out of SSA for so that both TGSI and the I965 backend, or the I965 VEC4 backend, both can share this really tricky code. Which means that either we have to keep around a ton of metadata that says, like, this 3-vector actually got allocated to the X, Y, and W components of some VEC4. And by the way, this thing got folded into here before we did that, and carry that all around, and then in the backend use it somehow. Or we can actually modify, or we can just modify the IR to represent it all directly, which I believe will be much easier. So that's why it's there. Thankfully, we can ignore it most of the time. In SSA, you don't have partial updates. You don't have mask rates. And also, it's trivial to have a separate absolute value, negate opcodes, and only fold those things in when you really need them for old backends and things like TGSI and I965 FS, so that they at least don't generate terrible code. They might not generate the best code because you're not taking advantage of hardware-specific things, but at this point, we don't really care that much about it. So the point is to make it not terrible. So that's why that's done. And that's how instructions work in TGSI, or that's how instructions work in NIR. But the next question is, once you've defined a model of how you add things, how you multiply things, and whatnot, how do we access inputs and outputs? How do we represent structures, et cetera? And there are two levels to this. Firstly, there are variables which are basically the same as they are in GLSL IR. You can use them to load. You can load a VEC4 component of a variable, and you have to build up dereference chain to get down to that VEC4. So you can load that into a register or an SSA value, which registers I'll get to next. You can store an SSA value into a variable. You can use them as samplers for texture instructions before we lower them down to texture indices, which is sort of another thing of let's make the backend do less. And finally, we use them for function arguments. We use them to, which most of the time they either will become inlined or will change those function arguments into global variables, which become global registers. So the backend won't have to deal with variables at all, but they're sort of an important concept at the high level. And if you want to do high-level optimizations like structure splitting and array splitting, you need to deal with variables. So some of the main, this is one of the points where it's really different from LLVM. And I've sort of avoided mentioning LLVM up until now, but it's, first of all, it's entirely logical. LLVM has a similar idea with structures, but it doesn't, you can always query a structure and ask where everything is laid out. With GPUs, this is really too complicated to handle. We could have the old VEC4 model where you actually want to convert things to you want to convert things to an array of struct representation, and you want to pack things. So if you have 4 arrays of scalars, you want to pack that into a single vector register. Or you could have a new scalar, or you could have like a new style scalar backend where you really don't want that. So the alignment is sort of too complicated between this, and we don't want to represent it at the higher level like LLVM does. So our addressing is entirely logical, and that also makes sense because we don't have pointers either. GLSL doesn't have pointers, so we don't have pointers. And also, finally, the main other thing, and it's kind of a minor point, is that because this is all copied from GLSL IR, we can represent GLSL level things that we've slowly been adding to GLSL IR without any extra metadata or stuff on top. So we have these variables and these structures that are basically source level, but we don't want backends to sort of have to handle that. We want to be able to lower these things and specify where each variable in the structure is actually laid out. So we also have the concept of registers. There are basically 2 modes. So registers are there for like the older VEC4 backends that I was talking about, where you want to go out of SSA before translating into the backend, so that backends don't have to worry about SSA. And they're also there for representing arrays of things once you've gotten rid of variables. So backends can lay out things basically however they want. I expect that there won't be too many special cases to this, and we can either do the standard traditional VEC4 thing, which is standard 140 packing basically, or we can do scalar packing, which is what i965 will want and what most new drivers will want, which is just lay things out contiguously in terms of units of 32 bits, which is so that's sort of the standard, but in the end, how you index things, what the index to the array of registers even means, all of that is up to the back end, and they can use it in whatever way they see convenient. If you have to care about the semantics of like where something is in an array, you should be doing it at the variable level. You shouldn't be doing it at this level. This is a lower level thing. So we have something that's basically higher level than LLVM and its get element pointer model, and we have something that's lower level and not quite at the machine code level if you're thinking in LLVM terms, but somewhere in between. Finally, the last piece to the puzzle of how NIR works is the intrinsics. The main thing to note here, they're pretty standard. They can take register SSA value inputs. They can output them. They can take variables, which is actually how we implement loading and storing variables. They're just an intrinsic. They're used for almost everything that can't be constant folded. The only exception is textures. They have their own separate instruction because I tried to do it as an intrinsic, and it's a combinatorial explosion. It can't be done. There are too many damn texture instructions. There are some additional bits like, can we delete this intrinsic? If it's a load, we can delete it. If it's a store, we can't delete it. Can we reorder it? If it's a load from, so for example, a uniform, we probably can reorder it. If it's a load from something else, if it's a load from, for example, for a temporary array, then we can't, not a temporary, but if it's a load from something else, we can't reorder it. The main difference, again, from LLVM is that these things are defined statically. They're sort of hard-coded, which is not as flexible in implementation, but because this is an IR that we ourselves are using and only ourselves, it's fine for our purposes. This is sort of a general point within NIR. It's only designed to be used inside of Mesa. So we can get away with using sort of simpler implementations and things because we're not being used as a library that make our lives a little easier at the expense of making it less portable, because that's not what we need from it. All right. So I've at Intel over the summer, I implemented I defined what this IR was going to be. I talked to the other Intel people about what they wanted from the IR. I wrote down and implemented most of the stuff so that you can print out textual representation of what the IR looks like. I implemented a front end for GLSL IR that takes GLSL IR, converts it into NIR. I implemented like a draft or like an original prototype of a backend that takes NIR and converts it into I965 fragment shader IR, and then that means that we can actually test it on real hardware. But there's still a lot more to do. Probably the most important thing is there are no optimizations right now. I have some stuff that converts it into SSA, but we need to, like Matt was talking about, we want to convert the I965 backend to use SSA, and then take our SSA stuff and shove it into the I965 SSA stuff, sort of cross the streams and get that working, which is going to be pretty cool. We need to have more precise semantics for Intrinsics. Like I mentioned, right now it only tells you if you can delete it and if you can reorder it, but I'd like to say like, oh, we can reorder this intrinsic with respect to this intrinsic over here, but with respect to this one, it's independent, which is something that LLVM already has. We need to represent some more things that people have been gradually adding over to GLSL. Like Matt said, we've been adding a lot of features, and the feature work is still ongoing, but we need to actually take those features that people are implementing and implement them in NIR as well, which is sort of a concern. And one of those is FP64. Also, we have tessellation shaders that are also coming up. I can't think of anything else right now, but that's sort of a problem with this. Everything is going on at once, and we need people, and it's almost like, stop, we need to fix our compiler before we go and add 20 new things to it. And other than that, yeah, so once we implement SSA, we want to do actually tons of optimizations. Like the examples of the DX programs that Matt was talking about, it's entirely trivial once we have SSA. And we just need to sit down and write all of the optimizations and implement this stuff now that it's been done. All right, so that was that was all of it. If anyone has any questions for me or the second part of what Matt was saying.
So you seem to have been really bothered about VEC4. I mean, did you ever try to think about, like, forget about VEC4, do everything like if it was a Scholar architecture, and during the scheduling and register allocation pass, there is way, and there is a small, tiny literature about it. There is way to actually do breaking down a VEC4, doing Scholar, doing all the compiler optimization, and when you do the actual register allocation and instruction scheduling, you go back to VEC4 by doing the instruction scheduling, pairing the instruction, but at the same time when you do VEC4, you also need to do the register allocation at the same time. So did you think about doing such thing like that?
So I think that was originally suggested. We talked about that when I actually came to Intel. And what I thought, the reason I didn't want to do that was that, first of all, it was one of the reasons we didn't do SSA originally in GLSL IR. If you look at like the README, it's like, well, if we do that, we could use this SSA, break everything up into scalars, and then at the end recombine it. But by doing optimization on scalar components, you might lose some of the vector information and actually make things worse. And also, I thought that most of the difficulty of working with vector stuff was going to be due to the partial writes. And with SSA, you don't have to worry about that at all. So I think that dealing with VEC4 actually isn't really going to be that much extra work for a lot of benefit for drivers that use TGSI. And so, yeah, we did consider that, but I think that it's worth the little bit of extra work it takes to convert these passes to use VEC4 semantics.
Yeah, like I say, very small literature about it, but last time I checked, like it's actually articles that are from the 80s. And they did a benchmark where they look at the original program that is actually written in VEC4. Well, it's not VEC4, it's VEC8 actually. It's a weird architecture that add 8 instructions at the same time. and then they break it down to scalar, do all the optimization, then do again a vec8. So they ran a bunch of program, huge list of program through their compiler and try to assess the number of instructions that they get from the original program to the optimized one that is being revectorized. And it turns out that with good heuristic and after a bit of work, we were able to really either be smaller, sometimes a little bit bigger, and on average, we were very close. So,
well, I mean, the point is I'm not comparing not doing any optimizations at all versus breaking it up. I'm comparing breaking it up versus not breaking up and still doing optimizations. It's the same thing. And the point is that by not breaking it up, we're not really precluding ourselves from doing any optimizations. It's not that much harder.
Yeah, so, I mean, we talked about it a lot. And, I mean, both when Connor was coming to do this work and for years before it would come up periodically. You know, in the existing IRs, it was just going to be really excruciating to do. And I think that once we get some kind of flat SSA IR that operates in whichever mode, you know, in Vec4 mode or in scalar mode, that, you know, we can make a step later to say, okay, you know what, let's you know, make a branch and do a bunch of work and try just going a scalarized route and do the experiments and see where it comes out. But we don't necessarily have to take all of that risk up front. I mean, so there's still the opportunity to do this. It's just that's like step 38 and we're on step 5.
and another question unrelated. So you said that you wanted to not care about pointers, but the same thing I'm pretty sure like GL Compute extension, maybe not the one that does exist today, but I think pointer at one point going to be a real deal. So for graphics.
Yeah, NVIDIA already has some extensions that basically give pointers, but they're, I don't know. It's not clear how pointers or pointer-like things are going to show up in GLSL. I don't know. It's not clear what that's going to be. It's not going to be the Wild West like it is in C, because it's just like, oh my God. Compilers have to do so damn much to deal with all the crazy things that you can and everyone does in C that I don't know, I really prefer to not see that come to GLSL ever.
And that's like half of what LLVM is.
Right. And I mean, and there will be something, especially as GPUs start to, you know, trend more towards shared address spaces and shared memory between the CPU and GPU, that you'll want to just say, I know where my thing is on the CPU, I'll just pass that pointer into the GPU and let it do stuff with that. But it's, yeah. The Magic 8 Ball says, future unclear, try again later.
Any other questions?
Okay, thanks. We are going to have another break.